Hello?
Sahib, can you hear us?
Yeah, I can hear you. Your voice is a little muted though.
Is that better now?
Yeah, much better.
I guess we're all set from our end as well. Apologies for the delay.
Oh, no worries. Okay, cool. Let me try and uh, share my screen. Oh, it says the host has disabled attendee screen sharing.
Right, so I've made you co-host.
Okay. Let me try again. Oh, there we go. Let's see. Okay, cool. Can you guys see this slide set? And let me also try and fix my Zoom. Sometimes I can't really tell if you guys are like if you put something on chat last time, I wasn't able to see it. Okay, there we go. Okay, cool. Oh, oops, wrong slide title. That was from last time, but good to be back. So we'll continue on our lecture series on quantum computing / programming. Last time we talked about combinatorial optimization, on what combinatorial optimization was, how it might be performed in kind of the long term when we have fault tolerant error corrected quantum computers. And we've talked quite a bit about the quantum approximate optimization algorithm, which is how we perform combinatorial optimization on near term quantum computers using this so-called hybrid or variational approach. Um, and and we described how that's sort of like an ongoing topic of research, which I hope intrepid young individuals such as yourselves would venture into as well. And a key part of the QAOA algorithm and its close cousins, generic variational algorithms, is that at the heart of it is basically we measure some sort of an expectation value. And so that's something we're going to go into quite a bit today. We're going to talk about near-term error mitigation. The last lecture series will involve the quantum supremacy experiment, which made quantum computers a bit more semi-famous than they were before, perhaps. But the focus of today will be error mitigation. So let's dive right into it. What I mean by error mitigation, specifically, I'm going to be talking about three types of error mitigation. So this is a generic quantum circuit, right? We start off in the zero state, let's say across 3 qubits, and the first qubit, well, in this case, I mean, because it's a controlled and it's a zero, it might not really do anything. But imagine if this was, some other qubit, and this was performing some controlled unitary operation on the remaining 2 qubits, right? So this is just some generic unitary on 3 qubits, essentially. And then finally, we just measure out what the 3 qubits look like. Well, at the end, basically, because quantum computers are probabilistic machines, we have to carry out this procedure many, many times. Let me also get my pointer out here. Okay, so we have to carry out this procedure many, many times and obtain some number of shots, right? That number of shots implies some sort of a sampling error. So that's one source of error that we get immediately just because of the nature of quantum computers being probabilistic machines, right? Being probabilistic computers. So we'll first investigate what sampling error means and how we can sort of control for it and bring it to some tolerable uh, region. We'll also talk a little bit about readout errors, which is something that can possibly corrupt your readouts, even if uh, your quantum computer behaves perfectly well. At the very end, some thermal noise or something could basically corrupt the sampling. Well, not the sampling procedure, but even if you sampled the correct bit, you could read it out as something erroneous. And then finally, we'll investigate the issue of gate errors, which is what if these unitary operations themselves were erroneous in some way? So all I should say that these are all topics of great interest and great depth, particularly things like gate errors. Of course, we will only be touching just the very surface of it. So, but I hope to give you a taste of what these topics look like and what they entail. And we'll talk a little bit about each of these things at least at the very basic level. Um, so to start off with, if you recall, last time we discussed the QAOA algorithm, in which the idea was that we're going to prepare some quantum state, uh, which followed some particular ansatz. We didn't say exactly what the exact state would be. That is to say, we didn't exactly specify what these parameters beta and gammas are going to be. Instead, these were parameters that we wanted to optimize for in order to basically maximize some expectation value of this cost function. This cost function over here was basically the cost function corresponding to a max cut problem, right? But more generally, max cut is just one of several possible combinatorial optimization problems. And you could, in fact, replace this with some other Hamiltonian that was solving some other kind of combinatorial optimization problem as well, right? Um, and if you remember from the exercise that we did last time, we were essentially measuring these expectation values using something like this, right? So we said that are observable. Uh, Remember, this cost function is really an observable, right? When we say that we're measuring something, we're implying that this thing that's being measured is in fact measurable, right? And so whatever's measurable is by definition an observable. We can observe it, we can infer what its value is, right? Uh, so that observable, we were computing its expectation value using the wave function simulator, right? Which is it's just an inbuilt handy tool in PyQuil, and as the name implies, it actually exactly simulates what the wave function or the quantum state should look like, and it computes the expectation taking in two inputs. Of course, at first it takes in the input with the program that specifies what state you're going to be producing. So in this particular case, it would have been the program uh, that produces this QAOA state, right? Um, and moreover, it also specifies what the observable is, or what the um, what the quantum operator is whose expectation value you want to compute. It's typically like some Hamiltonian, right? So in this case, it's the cost Hamiltonian corresponding to the max cut problem. And the way it does it is by simple linear algebra, right? So it computes. You all must have learned about these brackets by now, right? So this is basically like a row vector. This is your bra. This is your observable. This is like the cost Hamiltonian of the problem, and this is your ket. And so together these form a bracket. And essentially the idea is, like, I mean, once you compute this inner product, it just comes out to be uh, some scalar, right? And in fact, because the C is typically Hermitian, it's going to come out to be a real uh, value of some sort. Um, okay, good. So let's try to connect that particular procedure to our usual definition of expectation value in statistics, right? Now, of course, I mean, if we were able to do this process quite efficiently, that is to say, if we were able to compute these matrix products efficiently, then there would never have been any point in doing quantum computing in the first place, right? Like we could just we could just perform these matrix multiplications in a classical computer, and just compute these expectation values exactly, and we'd be done, right? But the whole problem is that as the number of qubits grows, uh, the dimensionality of these rows and these matrices grows as exponentially, right? Like the matrix is of size 2 to the n by 2 to the n, and this vector is um, a 2 to the n dimensional long vector, etc. So this computation essentially explodes very quickly, right? It grows exponentially in the number of qubits. So we want to estimate it using quantum computers. And because quantum computers are probabilistic machines, we are sort of uh, limited to only estimating them via the finite number of samples that we can obtain from the machine. So let's recall some basic statistics, right? When we say expectation value, well, okay, quantum mechanically, we know that this is really some matrix product of a row matrix and a column vector, but really it's also just the usual definition of the expectation value, right? So remember, um, the expectation value is really just the average value of some observable, right? So when I say like expected value of C, I basically mean like, okay, so what's the domain, um, what's the space of values that C can take values over, right? That's my X. What sort of like configurations produces some value of X, produces some value of C, right? So these are my configurations X. P of x is simply the probability of each particular configuration x, and C of x is the value taken by that variable in that particular configuration, right? And so a very simple example that you would read in your, intro to probability textbook is if C is like the number on a dice, right? And P of X is the probability of some outcome X, then if you have a fair dice where, of course, the numbers are 1 through 6 and the probabilities are all equal and uniform, then the expected value comes out to be like 3.5, right? On the other hand, you could also imagine like unfair dices, right? So, for example, it might be very probable for you to get the number 5, but very improbable for you to get the number 4. And I just cooked up these values really, but you could basically make up whatever values you want. But the idea is that if you tinker with these values and make it some non-uniform distribution, such as this, of course, that's going to change what the average value is, right? But in either case, like, I mean, we measure what the average value should be by essentially, if we know what these probabilities are, then we can compute what the average value is. And essentially, this is a prediction of what will happen if you roll this dice many, many times, right? Um, Record all the numbers that you get, and then take the average of those. Uh, this basically equation is predicting that this is basically the number that you're going to get, right? So good. So we talked about what that expected value is, which is the average, but also since we're talking about actually rolling out dices and computing their averages, we also want to get some sense of what the variance in this random variable is going to be, right? So remember, it is a random variable, right? Like I mean, C is a variable that can take values, 1 through 6 essentially. So we can equivalently ask, we could just as well ask, okay, well, what's going to be the spread in the values of this particular random variable? And that's captured by the variance, right? So we're saying that on average, so this is the average value of that random variable itself, right? C minus that average value squared gives you some sense of how much it deviates away from the average, right? So in our fair dice example, for example, 3 and 4 are closer to the average value, whereas 6 and 1 are much further apart, right? But we don't want like minus signs lingering around, right? So we don't want like 1 minus 3.5 to give us um, a negative number and 6 minus 3.5 to give us a positive number, so that that might confuse us and say like, okay, in some ways maybe because a negative number is smaller than a positive number, is 1 closer to the mean than 6 is? No, well, I guess in this case, 6 is closer to 3.5, but uh, let's just say that like basically we want to just compute the absolute distance between what one particular value is and its average, right? So that particular squared, and then of course we want the average of that thing, and that's why you can sort of write it like this. Remember, the average of something is basically just the probability of the some configuration times the value of what that random variable takes in that configuration, and then you sum that product over all possible configurations, right? And of course, there's generalizations to this in the continuous case. I'm hoping, by the way, that this is pure review. If I'm going too slow or too fast, please let me know. Um, but I just wanted to recall like a few basic factoids about this elementary statistics because it's going to be useful for what we're discussing. In fact, what I really want to make the impression, impress upon you all is that it's really just this elementary statistics that we're talking about. There's nothing. I'll only bring in quantum at the very, very end, and hopefully you'll immediately see that like we're basically just talking about dices. Nothing really much deeper than that, right? But anyway, okay. So we have this variance, and this computes the spread in the value of some random variable, such as the number on a fair dice, which we can compute, and it'll come out to be something like 2.92. We could also compute it in the case of our unfair dice, and it'll come out to be 3.03. So intuitively, what this means, uh, I, you know, I was talking about like how it sort of captures the spread of a random variable. Here's maybe a more concrete way of thinking about the same thing, right? So empirically, experimentally, how would we compute the average value of rolling out some dice, right? Like we might follow this following procedure. We might roll a dice out some particular number of times, n times, and we would just record all the values, right? Like the first time it was a one, second time it was a three, third time it was a two, et cetera, et cetera, et cetera, right? And so we would do this like say 100 or 1,000 or 10,000 times, uh, record all the values, and then we would compute and report the average of all those values, right? And so that thing is what I'm calling C bar. This is like my empirical or experimental average of the dice that I rolled, right? Uh, and so notice that that itself is a random variable, right? So I am basically saying, okay, like the value of this random variable C on the first roll, right? That's what I'm calling C1. And the C, it can take on in the fair dice example, it can take on any of the six values with equal probability. In the unfair dice example, it can take on, say one with whatever probability I specified for it, etc., or six with whatever probability I specified for it, and so on and so forth, right? Um, so this is basically a sum of random variables, and then I'll divide it out by the total number of times that I actually rolled up the dice. Um, and so this thing is a completely independent random variable in its own right, which has something to do with my original random variable C, um, but it strictly speaking isn't exactly equal to that. Nevertheless, this provides me with some approximation with what the true expectation value should be. Remember, so I said a couple of slides ago that when I compute something like this, really what it's saying is that theoretically this is sort of my prediction for what will happen if you measure this random variable many, 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 many times, and then compute its average, that the average that you compute should be theoretically very close to the number that I compute using this equation, right? And so that's what this approximation sign stands for. Now, intuitively, it should be true that the more number of trials I have, or in other words, the more number of times I roll the dice, the closer and closer my average, my empirical average, should get to the true computed average, right? What the theoretical expected average should be. Uh, and so there's some nice math that sort of makes this a lot more rigorous and says, okay, in the limit in which the number of trials goes to infinity. Like if you just, rolled out a dice infinitely many times and then computed the average, then yes, this thing will become exactly equal to that. Um, there's another nice property about this, which is that if you take the expectation value of this particular observable, it comes out to be exactly equal to the theoretical um, value of the original random variable C. And so whatever that holds, we call our estimator an unbiased estimator, right? Because its expectation value is the same, the expectation value of this estimator of C is the same as the expectation value of the original thing that it was trying to estimate in the first place, okay? Um, so that's what I mean by this, right? So if the expectation, so this is a random variable in its own right, right? Its expectation value turns out to be equal to the expectation value of the original observable C, which is what I've been writing as, C within the brackets. And I write it deliberately because, uh, I mentioned a couple of slides ago that our quantum mechanical way of computing these expectation values, which was, if we do it on a pen and paper, we would basically sandwich some matrix representation of C with whatever state that we're computing it in. Uh, we'll sandwich it as a row and a column vector. Whatever number we get out from that, it should basically be the same as sort of like computing it in this kind of more traditional classical way. Um, that's basically what this series of equalities really means. Uh, but finally, the variance of this new random variable, of this estimator, this basically is 1 over n times the variance of the original random variable. Okay, and that's significant, right? So basically what that's saying is that if the variance in some sense is capturing the spread of values around the center, or around the average or the mean of this random variable, then basically what this is saying is that that spread should get smaller and smaller as we increase the number of measurements or trials or experiments or whatever you want to call it, right? Um, and so, the procedure to sort of make this come out a bit more alive and intuitive, hopefully, is, you can imagine doing something like the following. So, the goal is to compute the average of some observable C to within some tolerable error, right? And by error now, I mean specifically this variance, right? So because the variance, like we said, it's basically the spread around the average value, right? Notice that if n goes to infinity, then this variance goes to 0, right? But of course, no one can ever perform an infinite number of experiments. And so what we can do instead is we say, okay, what is my target variance? Like how much spread in my values can I tolerate? This is typically like, maybe uh, it's entirely up to you, right? Like, I mean, people desire a certain number to within some tolerable approximation errors, given perhaps by your device apparatus or given perhaps by the necessity of the science that you're performing. Like, for example, chemists, quantum chemists, and others like try to. I think they define something like chemical accuracy, which is a standardized unit of, like how much like what sort of like error they're willing to tolerate when they're reported a particular value, right? So this could be like 10 to the minus 2 or 10 to the minus 4 or 10 to the minus 10 or whatever it is, right? It's some value that you will decide. And then based on that, you will decide how many numbers of shots or how many trials you have to take in order to hit that target variance, right? And what this spread in C bar looks like essentially is as follows, right? Um, so remember now that, we're trying to compute the expectation value of the original random variable C. What we have access to experimentally, of course, is only C bar, right? Because what we can do is, in essence, what all that we can do is we have some machine that, if you click on it, or if you call it, people we've been talking about like an oracle or a black box in previous classes. Like, this could be some black box, right? It's like a coin toss or whatever it is, right? It's like you call this thing and it gives you a number, right? This is like the abstract formulation of what we're talking about here. So this thing, this random, this thing that spits out a value for the random variable, uh, that's the random variable that we want to estimate, but we only have access to this machine and we can only call it some finite number of times, right? So what do? We can imagine doing the following. We say we'll repeat the following over several experiments. In each experiment, we will repeat the following over several trials, right? So there's two repetitions over here. So so basically for each trial, we'll basically roll out a dice several numbers of times, right? Say n times, and we'll record the value each time, right? So like, I mean, let's say we rolled out a dice 100 times, and we record the average and it comes out to be something like 3.1, right? We'll compute the average of these rolls, and then we'll basically record all these averages. So in the first experiment, I did a trial of, 100 rolls, computed the average, noted down the average. Now I'm going to perform a similar experiment all over again, and I'm going to compute similarly, the average of 100 different rolls. Maybe it comes out to be 2.9, right? I'll note that down again, and then I'll repeat the same thing over and over again, many, many times. Uh, and now I have this huge list of these averages, right? And now if I plot the distribution of what these averages looks like, um, it will look something like this. So notice that notice two things, right? So in both the case of the fair dice and the unfair dice, it looks like a bell-shaped curve, right? Um, and in the case of the fair dice, it's centered around its average value, which is 3.5. And in the case of the unfair dice, it's centered around its average value, which was something like, we computed it to be 3.6 to 3.65. Um, and that's not a coincidence. Basically, there's a theorem called the central limit theorem that says that both of these graphs should look bell-shaped. So more specifically, they look like a Gaussian curve, right? As these number of trials and experiments goes to very, very large numbers. Um, so that's basically the idea, right? So like, what I have on this histogram is basically my estimate of what the average value of that variable is, right? It's an estimate of this thing. And just like any estimate, it has some experimental error, right? And so this basically the sort of like the width or the fatness of this normal or bell-shaped curve is what basically the variance in that variable C bar was representing, this thing over here. The more n I take, the larger of these, like shots I take, basically the thinner and thinner I should see this getting. Okay, and that n basically, by the way, is over here. So that's basically the point, right? So like, I mean, in other words, like if I want to have a reliable estimate of what my, of course, like I know because I already was able to compute it, that the ideal value is 3.5, right? But you can look at this distribution and you say that, okay, if like in a typical experiment, if I do many, many rolls and I compute the average, yeah, the empirical average that I calculate using a procedure like that will fall somewhere in this region, but there's a small probability that I might get, some number that's like at over here or some number that's over here. And so in order to diminish that probability more and more and more, you want to take a larger and larger, number of samples to average over. That's basically the idea. Okay, good. So now let's bring it back to the quantum land, right? It's basically the same thing. Remember, so in QAOA, for example, we have some ansatz that we're using to prepare our quantum state. Um, and in that quantum state, we want to measure the value of some measure the expectation value of some observable, in this case, the cost function. And we talked a little bit about how we estimate any variable via sampling, right? And just, when we estimate this particular variable, we also need to keep in mind the variance of that variable. Um, and the only real difference when it comes to quantum is that basically this P of X, in the case of dies, I just specified what those values were. In the case of a fair dice, it was like 1/6 for all the outcomes. Um, in a quantum computer, these X's are, of course, the possible bit strings that you can sample, right? So um, if you have a single qubit, then this is just 0 and 1. If you have two qubits, then this is 0, 0, or 0, 1, or 1, 0, or 1, 1, right? And more generally, if you have n qubits, then this is basically the sum over all possible 2 to the n bit strings. P of x is the probability of sampling some particular bit string, and it's given by this inner product with the state psi that you actually produce. And x, you should replace that with whatever bit string that whose probability of sampling you're trying to compute. For example, 0, 0 in a 2-qubit state, or 0, 1, or 1, 0, or 1, 1. Just that inner product by itself is a complex number, of course, and so you would take the absolute value squared, and that's what gives you the probability. This is like the Born probability of sampling from a quantum device, right? So good. Okay, so that's basically it, right? Like, I mean, C is some observable that we can measure on a quantum computer. P of X is, C is some observable. When I say C is some observable that we can measure on a quantum computer, what I mean is that C is some observable that takes values over bit strings. Okay, that's it. Because X is a bit string, right? And a quantum computer basically is a machine that allows me to sample bit strings with different probabilities. Okay. Ultimately, it's just a device that when I query it, or when I tell it to give me a sample, it's just going to give me a bit string. Okay. It's the whole idea of like why quantum computers are powerful is because it can prepare certain probability distributions over those bit strings that are hard to prepare for classical computers, right? And that's why we believe they have a certain computational advantage. But basically speaking, all they do is give me a bit string, right? And so the probability of sampling that bit string is given by this. And so C is, whatever variable I can imagine that takes values over that bit string. I can compute its expectation value. I can compute its variance. Um, and, experimentally, again, all I have access to, of course, is uh, like a finite number of experiments over which I could uh, compute what the variable takes on, right? In this case, n could be like the number of shots, right? So if I run a quantum computer, like I specify a circuit, I'll run the quantum circuit once, measure out the qubits. Those give me a bit string, right? That's my experiment one, or that's my run one, or first shot, or whatever you want to call it. Then I'll run the quantum circuit again. I'll measure out the qubits. Again, I will measure out, some bit string, et cetera, right? So I just do this many, many times, n times. I measure what C is as a function of those bit strings, and I compute its average. So the procedure is exactly the same of how to compute this expectation value to within some tolerable error. Basically, we'll repeat the following over several experiments. Instead of rolling out a dice n times and recording the value each time, we'll basically run a quantum circuit, we'll measure the qubits, we'll compute the value of the observable, and we'll record the value each time, right? And we'll compute the average of all these n shots. I'm calling them shots instead of rolls now. Record all the average of these n shots. The distribution should look basically bell-shaped. And now if you compute the average of all these averages, that should look very much like, that will be a much sort of, kind of like, a good estimate of what the original C should be, right? But in practice, people often just stop at this first part, right? So like basically, if you really wanted to see what this distribution looks like, again, because of the central limit theorem, this should look bell-shaped. Um, like you can do this, and then if you really have the time and the QPU hours, really, you would maybe also do something like this, and then report the average of all those several experiments. But really, in practice, what people do is like they specify some number of shots. Again, computing, the number of shots that will produce some tolerable error. Um, and so once they have that, then they will just report what that expectation value is, using that many shots, essentially. But if you really wanted to estimate, like concretely, experimentally, um, evaluate what your experimental standard deviation is in your standard error of the mean is, et cetera, then you would do something like this. But essentially, I just wanted to replicate the same thing over here, just to impress upon you that this is really, we're just replacing dices with measuring some qubits, but they're both basically probabilistic processes at the end of the day. And so, an example of how you would compute the value of some observable and record the value each time is, I guess, a little bit, slightly bit more complicated in the case of qubits. In the case of a dice, of course, you just read the number that lands, that's facing you, right? So if it lands one, then you record one, and if it lands six, then you record six, etc. In the case of qubits, it depends on what you're measuring, of course. But if you're, say, measuring the observable z, uh, and you read out the bit string 00, then if you remember from last time, z times zero, z acting on zero gives you just like +1 times 0. Z acting on 1 gives you -1 times that state again. And so, this basically takes on value +1 and 0 and -1 and 1. And so +1 times +1 is 1. +1 times -1 is -1. And you can work out all the other numbers similarly, right? So this is how you would record the values. You read some bit string 00, you compute what that observable, what value that observable takes on that bit string, um, and you record the value each time. And you basically have some large number of shots, n. Whatever number, whatever sequence of numbers you get over here, you would compute the average of that, and that will give you an estimate of what this observable ZZ looks like in the state that produced these particular bit string samples. Okay. Any questions about sampling errors or?
So Swaib, just a clarification for the last step over here, compute the average of all these averages. You said we would need more QPU time. Isn't that just a classical computation? So I'm missing something.
Oh no, what I mean to say is that, like, I mean, if you, so that, yes, but what I mean to say is that, like, I mean, typically what people will do is uh, they will only have one such experiment, right? So you will just specify n shots, right? And you will say like, okay, n shots is 1,000, and you would just run your quantum circuit like 1,000 times, and you would compute the average of those 1,000 shots. What I'm saying is that, if you wanted to replicate, and this is something we'll do in the exercise notebooks as well, so maybe it might become clearer then. But all I'm saying is that, like for example, if this was a quantum experiment, not a classical one,
Got it.
then this is just one experiment over, say, 1,000 shots, right? And now I'm going to do like several of these experiments. So sometimes, we do this kind of thing when we're benchmarking our devices just to make sure that, um, like, I mean, we're like, say, like you're performing um, tomography or something, or, like, I mean, you're just like observing some observable whose expectation value you can compute, right? And to really, really be sure that your QPU is producing this expectation value in the correct tolerable range, um, you would measure, like you would perform an experiment like this using n shots, right? Say 1,000 shots or whatever. And then you would repeat that experiment many, many times.
Got it.
And then you would plot your averages and compute the average of all your averages. And this better not have a bias, right? That's the point. that this average should really be pretty close to, the ideal expectation value.
Right. Thank you.
Yep. Thanks for the question. Um,
Anything else?
okay, cool. So, going sort of backwards from the quantum circuit, like we started off with sampling errors, assuming, like our quantum device was perfect. Sampling errors is, of course, something we cannot avoid just because of the probabilistic natures of quantum computers. But now let's investigate, let's see what happens if we have some sort of a readout errors, right? So we'll carry out, like, you could imagine doing the same kind of dice experiment, um, in which now instead of like actually rolling dices, let's say we're rolling dices on a computer, right? And so we're encoding all our dice states into bits, right? So one gets mapped to all zeros bit string, two gets mapped to one, et cetera, et cetera, et cetera, right? This is like, I mean, this is all like, the binary version of this number minus one, essentially. And of course, the measurement probabilities then are just, whatever the measurement probability of one is. If we program our computer to be in such a way that, the probability of this bit string comes out to be exactly equal to whatever the probability of one is, et cetera, then we sort of replicated the same experiment, right? Um, Now, what happens if we have the following situation? Let's say that one of these bits, so we have like 3 bits over here, right? Let's say that like this last bit is faulty. And what happens is that even if you sample this bit, to be a zero, uh, when you actually read it out, there is some probability that you're going to misread it. Okay, so what that means is that even though the true state of this bit is zero, uh, the probability that you actually read it out as a one, even though it was a zero, is small, but non-zero, right? So that's basically what we mean by a readout error, right? So which is basically saying, uh, you'll misread it as some other value, even though it truly is, some other particular value, right? And this sort of thing does happen on quantum devices, right? Like, I mean, remember that like sampling is something we cannot. So the sampling probabilities are something that we have to work with, right? Uh, I just noticed a question over here. Let me quickly read it. If I want my variance very close to zero, does that mean I have to just increase the number of shots? Yeah, basically you have to increase the number of shots. That's kind of, and let me say one other thing about that real quick, which is that, so typically when people, in practice estimate the number of shots over here, uh, they will also have some sort of estimate for what this particular variance looks like. So if you notice, if you go back to the definition of this particular, um, of the original C variable, right? This is like, the difference between the variable and its expected value squared, right? And then the expectation value of that. So if I have something like, say, the max cut Hamiltonian, uh, notice that, C is very strongly dependent on what these weights are. So in practice, a lot of the times, and like there's these weights, and then of course there are these Pauli operators. The Pauli operators have some nice properties which make, their algebra kind of like simplified in some ways. And so typically, the costs of, the variance, the dominant contributions to the variance comes from these weight factors. That's what people worry about, when it comes to, um, how many shots you need in order to estimate something to within some, tolerable error. And that's one of the like big things about, like, that was one of the earlier sort of, um, I should say, big complaints around variational algorithms is that, if you look at, for example, I think chemistry Hamiltonians. I'm not a quantum chemistry expert by any means, but I remember that people would complain quite a bit about, like, oh well, if we encode these Hamiltonians into qubits, the these factors are just so large, that the number of shots that I need has to be quite a bit, in order to cancel out that large number in the numerator. Um, and so that was, like, I mean, if we have like a squillion shots to take in order to get like a reasonable tolerance or say chemical accuracy or whatever, then it becomes pretty practically worthless pretty quickly, right? So people invented all sorts of ways around that, like, I mean, shot frugal learning and whatnot. We're definitely not going to go get into all of that here today. But to, at a very basic level, yes, that's like a constraint that you absolutely have to work around, and that's something uh, like this equation always holds, right? So there's no way of getting around this equation, as far as I know. So yeah, okay. But to return to readout errors, um, yeah. So like, I mean, so even though, so like, we can never get around the sampling errors that we have inherently on any probabilistic machine, such as quantum computers. But even if we sample something according to the perfect sampling probability, right, uh, there is still a chance, a non-zero chance, that the bit, even though it was sampled like, according to the ideal distribution, it was read out incorrectly, right? Um, and so let's see how that affects our our sort of observed probabilities, right? So all we have access to experimentally is, of course, that we read something, right? So the quantum device measures our quantum state and it produces some bit string. And this bit string is some string of zeros and ones, of course. And now, we'll have, we can see that, like, I mean, this P of zero is really, strictly speaking, P, the probability of uh, our bit being read out to be zero, okay? And this probability of being read out to be zero, if you consider the law of total probability, this is basically the sum over all possible configurations again, right? Of being, of our bit having been sampled in whatever uh, uh, possibilities there are. This is essentially just basically saying, if you have, um, yeah, it's basically just the law of total probability. Like, if you have some sort of sample space, and you're considering the probability of some event, then you can essentially say that the probability of that event is the probability of this event, and some other event, plus the probability of this event, plus some other event, and you sum over all those other events, such that they sum totally to the entire sample space. Guys, give me just 1 minute, please. Hi again. Sorry about that. Okay, so this this particular equation, I hope, is you guys have seen this before. If you haven't, we can discuss this a little bit. But essentially, for the case of a single qubit, all this means is that, if I really just write it out in full gory detail, it's something like the probability of my qubit being read out as zero, and the fact that it was also sampled as zero, plus the probability that it was read out as zero and that it was sampled as one. And I just realized that I have a typo over here, because this really should have been a little bit uh, uh, more than just this. No, actually, sorry, I take it back. This is exactly what I had in mind. So now, if basically this is now, like, now this is a sum of two joint probabilities, and every joint probability I can decompose into conditional probabilities, right? So P of probability of A and B is basically probability of A given B times the probability of B. And that's all that this is saying. This is basically saying that the probability of my bit being read out as zero, and uh, and the fact that it was actually sampled as 0 is the probability that it was read out as 0, given that it was sampled as 0, plus the probability that it was, times the probability it was sampled as 0, plus likewise, I will just simply decompose this into its conditional probability. Okay, good. And so now, what I'm really interested in are these true sampling probabilities, right? So these were the probability that my bit was actually sampled as 0. This was equal to, this kind of like inner product that I can compute using linear algebra, right? Um, and likewise, this particular sampling probability is again something that I could compute in principle from first principles. But this is something that ideally I would like to measure on my quantum device, right? Like otherwise, if I were to always just measure it using pen and papers, then we don't need a quantum computer, right? The whole idea is that we'll be able to compute these sort of things using quantum computers without having to compute it ourselves on a pen and paper. Um, but if our quantum device is erroneous and it can give faulty readouts, then we need some sort of a way to correct for that. So the way to correct for that is as follows. So I can generalize this previous statement, where I had, say, as an example, the probability of 0. I can say that the probability of my bit string being read out in as in fact, like the probability of all my of my measured qubits coming out to be in some configuration that give the bit string X is really the sum of the following thing, right? So it's the sum of conditional probabilities where my read out bit string is X, given that the true sampled bit string was Y, times the true sampling probability of Y, right? And so I can express this in matrix form. This is basically the equation of a matrix, right? So if like there are like 2 to the n possible values over here for X, right? Like, so as an example, like if I have 3 qubits, then this is, an 8 column vector, an 8-dimensional column vector. And this is an 8 by 8 matrix, right? So this is basically saying that you actually sampled the bit string 000, and you also read it out as 000, right? And this is saying that you sampled it as a 111, but actually all these bits, you read them out in the wrong manner, and you read them out as 000. And of course you have everything in between, right? So you have like P read out as 000, given that it was actually 010 and 011, and et cetera, et cetera. And likewise over here, right? So like this is like you read it out as 111, even though you sampled it as 000, et cetera, right? So this is what we call like a confusion matrix, right? Where on the where we're saying like we'll sample, like there was a true sampling performed, like the true state of the qubits was this thing on the right hand side, but we actually read it out like this, okay? Um, and so this thing on the right-hand side, this is of course what the true sampling probabilities are. And in a typical quantum computing problem, this is like these probabilities on the right-hand side, that's what we're actually interested in, right? Um, but now, if this is something that we can, if this is something that we can uh, compute experimentally, right? So this is like what we'll actually have access to experimentally, right? We can simply run our quantum circuit um, a great number of times, and we can estimate how many times, like we'll count the number of times we found the bit string 000, and divide that by the total number of shots, and that fraction gives us an estimate of what this probability 000 is. And we will likewise do that for each of the bit strings. And that gives us an experimental estimate of what these probabilities are. And likewise, we can compute what this confusion matrix looks like by doing the following. So what we will say is that, okay, we will essentially, prepare each of these ideal states on our quantum device, and then we will read it out. right? So for example, in the case of 000, we will essentially do nothing at all, right? Because our quantum states always start off from the state 0. Um, and then we will just read it out. And if that comes out to be, and we'll simply count the number of times that we actually read the bit string 000. If we sometimes read the bit string 010, then we'll basically say probability of 010 given 000 is in fact non-zero, right? So it's whatever fraction of times we compute, we found the number, the bit string 010. And likewise over here, right? So we prepare 000, which is just the starting state. We do nothing on the quantum device, and then we just measure all the qubits. And maybe some, 5 out of a million times, we'll measure the qubits to be in the state 111. And so in that case, that this estimate would be like 5 over a million or however many shots we get. This typically is pretty small. Um, Sometimes we'll get, a number like this. So over here, what we'll do is, because our qubits start off in the 000 state, we'll perform X operations or bit flips on each of them. Um, Having performed bit flips on each of them, we will now measure them out. And if we find, ideally, we should only find this particular thing, right? So we should only, like, let's say we did this a million times. If we only measure this bit string, then there's no readout errors over here. This is 1, and everything else on this column is 0. But if it turns out to be the case that sometimes, for example, we see the bit string 000, then this will count the number, the fraction of times we actually see that bit string, and so forth. So that's how you estimate this confusion matrix. This is something you get from running your quantum circuit. So important point, which is something that you'll use in your exercise, but this is something you get from your quantum circuit. This is something which you get from devising 2 to the n different experiments. Okay, so I say that deliberately because it's kind of like obvious now then that if you do this kind of thing, this isn't really going to scale very well because it scales as 2 to the n. It scales exponentially. So you're killing off any potential quantum advantage you could use. But nevertheless, this is something that people use in the near term to sort of correct for readout errors. There's also other clever techniques where assuming some sort of like nice properties about your readout errors, you can maybe get away with something that only scales linearly and not exponentially in the number of qubits. We won't get into that today, but hopefully you get a taste of what these readout errors look like. But anyway, the point is that once you know what this column vector is, and once you know what this matrix is, then writing it out as a matrix equation, then it's basically a simple deal to sort of solve for this column vector. You simply invert this matrix, and you multiply the inverse of that matrix by the vector that appears on the left-hand side, and that gives you the true sampling probabilities. And at that point, you can sort of go back to your expression for what the expectation value is and plug in these true expectation values, knowing what the value of the observable is in each configuration. And that will give you a much better idea of what this true expected value of this observable should be. So any questions about readout errors? Okay.
There's one question, I think.
Okay.
हमारे पास मेजरमेंट पे होते हैं तो जो आप कह रहे हैं कि पूरा कंफ्यूजन मैट्रिक्स बनाते हैं तो पर मेजरमेंट जो हम लोग परफॉर्म कर रहे होते हैं उसके ऊपर ही उसको पूरा परफॉर्म करते हैं लाइक मल्टीपल मेजरमेंट्स करने के लिए मल्टीपल इंस्ट्रूमेंट्स होते हैं या हम लोग एक
No, एक instrument होता है. So basically the idea is like you're going to so you're going to do it like this, right? Like, I mean, आपके पास, let's say you just have like these 3 qubits, right? So in experiment 1, you do nothing. And then you just read out all the qubits. And let's say you specify some number of shots, like 1,000 shots or 10,000 shots. And if you find, and basically, you just, you calculate what your, or you just like, find out, you record what your bit strings were in each of those 10,000 shots. Remember, like your program now is just do nothing, right? Like identity on 0, identity on qubit 0, identity on qubit 1, identity on qubit 3. You read out 1,000 different shots, right? And let's say that 950 of those shots gave you the bit string 000, then this number is 950 divided by 1,000. And let's say in 10 of those shots, um, qubit 3 had the state 1, right? And qubits 1 and 2, or let's call these A, B, and C, right? So qubits A and B had 0 and 0, and qubit C had the state 1. And this was only true of like 5 out of the 1,000 shots. Then the bit string, then the probability P001 given 000 is going to be 5 out of 1,000, right? So that's basically one set of experiments, right? And using the same device, it's important that you use the same device, right? Because uh, this is all characterizing the same device that um, that you used to run the quantum circuit that produced these probabilities in the first place, right? So these probabilities, I'm assuming that like, okay, you ran some quantum circuit on this device and that quantum circuit produced these probabilities. And so if I want to characterize the readout errors on this particular device, uh, it's only for that device that this thing holds, right? So there's no, maybe there's some other sort of like clever way you could parallelize this, but I don't really immediately see how. I think is your question, right? If I'm not mistaken, is like you're wondering like if I had like say many parallel quantum devices, could I sort of increase the efficiency of this computation in some way by parallelizing this somehow? Was that your question?
Yes.
Okay, yeah, yeah. So I mean, it's a great question, but I think so. So I will say that when it comes to parallelization, one thing that people, that you can do is you can go back to say something like this, right? So you want to compute the expectation value of C, right? Now, typically over here, C is, composed of the identity and ZZ terms. And the thing, the nice property, the really nice property about these operators, like both the identity as well as the ZZ terms, is that they all commute with one another, right? So ZZ is diagonal in the computational basis, and 1, which is the identity, is also diagonal in the computational basis. So all of these commute with one another, right? But this doesn't necessarily have to be the case. You won't find it in combinatorial optimization, but you will most definitely find it in quantum chemistry. You will also probably find it in quantum machine learning. That basically sometimes you can have Hamiltonians that are like sum of ZZ plus XX plus XY plus YZ plus, other whole, like, a whole jumble of stuff, right? And so those terms don't commute with one another, right? So for example, a ZZ might commute with XX, uh, but it might not commute with, like, generally speaking, like, for example, ZZ won't commute with a ZX, right? Um, and so what you have to do in those cases is you say, okay, I have to first reserve my quantum device to only measure the ZZ term, and maybe whatever else commutes with ZZ. So for example, an identity or IZ or ZI or whatever, right? Um, and then I have to do a separate run in which, and we'll see why, by the way, in the exercise, then I'll do a separate run in which I'll measure ZX and everything that, maybe could be measured along with ZX. Um, when it comes to doing stuff like that, there you can imagine some sort of a parallelization. You can say like, okay, I'm going to measure ZZ on this particular quantum device, and I'm going to measure ZX on this other quantum device, and I can completely parallelize those processes, right? So we've actually done that at Rigetti. Like, I mean, we did something like that with Um, Earlier this year, I think it was, I was actually taking some time off at the time, but I think it was the context of some QML stuff that we did with Xanadu, which is a Canadian startup. Um, you should look up Penny Lane, by the way, which is something we worked on with them. A quantum machine learning library, um, open source. But again, like I mean, the idea is similar. That like yes, like you want to compute expectation values, you cannot really compute all the expectation values in one go. So sometimes what you could imagine doing is you could parallelize that process. But once you pick one quantum device to measure, say, one set of operators within your cost function or within this observable that we're calling C, then you're sort of committed to that device, right? And so in order to account and mitigate for the errors on that particular device, you have to do something like this. So you have to know uh, what the like you have to know, like, okay, these were the readout probabilities on this particular device. And so these are probably erroneous, assuming some sort of readout error. And so in order to mitigate for these erroneous probabilities and work out what the true sampling probabilities were, I have to characterize this device. And I would characterize it, by computing this particular confusion matrix.
So just a follow-up question to that. So when you discuss this process for doing it for non-commuting measurements and then running it in parallel, the distributions that we are constructing in each of the individual groups or individual nodes would be a smaller set of the joint distribution, right? So it would be P of AB in one end and let's say P of CD in the other end. So essentially at that point we get a P of AB and we get a P of CD. We still don't have the full joint P of ABCD, right? And that makes sense because they were non-commuting measurements. But is there an issue, or would there be a reason where we actually do want the entire distribution P of ABCD, but this process is only giving us only this smaller joint distribution?
So it depends, right? Like, I mean, if say like you're measuring observables over, let's say that A, B, C, and D we're referring to not a collection of qubits, but rather qubits themselves, right? So A, B, C, and D are qubits, 4 qubits, right? And so it depends in the following sense, right? So if your Hamiltonian breaks up into um, operators that are only defined on qubits, or okay, let's call them subsystems. A is some subsystem of qubits A, and B is some other disjoint subsystem or collection of qubits B. C is another disjoint collection of qubits, etc. uh, then I mean, if your operators that you're whose expectation value you're estimating is only defined on A and B, uh, then, well, for one thing, like I mean, they completely commute with the operators that are defined on C and D, right? So those two things, like you could actually do on the same device if you have enough number of qubits, right?
Mhm.
Now, if they're overlapping, right, uh, then it depends, right? Because like I mean, really what you're measuring, um, like let's imagine that this was a sum of two such terms, right? Like I mean, like let's say this was like z1 z2 uh, plus x2 x3, for example. uh, z1 z2 does not commute with x2 x3, right? And z1, let's say, like I mean, like obviously they have the overlap of qubit 2, right? So you could, in principle, completely do this in a parallel process, right? Like you don't need, the qubit 2 of your problem to be the same physical qubit of your device, right? So you could have, like, let's say I actually had like two quantum computers, both of them having 2 qubits each. I could solve this problem on that quantum computer, right? I could basically say, because I really only have like two body terms here, like two local terms, right? So I can compute like z1, z2, um, and then, well, I guess okay. So this is also going into territory. No, probably not. I take that back. I take that back because you're in the most generic sense. Like you would need, you have to produce. You're assuming that you could produce like sort of like some 3-qubit state, and then take like, I mean, like some reduced expectation value. So no, you can't really get away with like 2 quantum computers with 2 qubits each. You would probably still need like, 3 qubits each. But you could nevertheless, I mean, like prepare the same states from the same circuits on both those devices, right? And I can't really see any reason why, uh, you know, I know I'm going to kick myself later on if I think of a very obvious reason for why you can't do this, but I really can't think of anything off the top of my head that something that prevents you from, say, uh, measuring Z1, Z2 on, 1 QPU that has 3 qubits, say. Let's say like, we had 2 QPUs, 3 qubits each, and we were running a 3 qubit program, and we wanted to measure the observable Z1, Z2 plus X2, X3. Um, and on QPU A, you run this program, let's say 1,000, for 1,000 shots, you compute what Z1, Z2 is, and in QPU B, you compute, X2, X3, and you compute the expectation value there. Now, the only difference is, of course, these are 2 different QPUs, right? And so they have 2 different confusion matrices, right? Uh, 2 different, these observed distribution, sampling or readout probabilities, right? Uh, and so you would have to like, like, I mean, you would have to characterize the device, you would have to characterize those 2 devices separately. But once, if you do that consistently, I don't really see a reason uh, why you need to, why there's anything else really that's involved there.
Well, so my concern is just that when I've run these 2 different entities, or 2 different processes, in one case I've constructed a joint distribution for AB, and in the other case I get a joint distribution CD. And my concern is, would there be any reason where, let's say, I'm actually interested in getting the joint distribution ABCD together? Because this process is only allowing me to construct kind of a pairwise joint distribution, right? What if my really end goal is that, hey, I want the full 4-tuple joint distribution?
Right, but I guess the claim here is that it shouldn't matter, right? Like the only time it should matter is if you do have an observable that that takes on values on all 4 of them. And I guess like, I mean, in some ways, like, I mean, each of your observables takes on value on all 4 of them in the trivial sense that, when you have something like x2, x3, then you're applying the identity on the first one. But that's sort of like error mitigation for free in that case, right? Because you just say it's the identity, so whatever, I'm just going to set that to 1 or whatever. Now, if it was the case that you had to care about the joint probability distribution, um, then yes. But like, I guess, translating your problem there, I'm basically, what I'm thinking is, and what I'm sort of fairly sure about is that, yeah, you don't necessarily need to care about, um, like, I mean, okay, so I guess like let's think about it like this, right? So we can say like, okay, like, so C is, properly speaking, say a distribution over 4 different systems, A, B, C, D, right? And so these configurations will sum over, um, all possible configurations over that entire, space, like configurations over those entire 4 elements. But let's say your C breaks up into, in some parts, like it only concentrates on A and B, and it acts trivially on C and D. Um, then those parts, like, I mean, let's say we only have the identity over C and D, then because it's the identity, you can basically sum up that part trivially, right? Like you can just sort of like analytically sort of factor that part out. And you just say like, okay, it's like the probability of distributions over, uh, you see what I'm saying? Like, I mean, like basically I can sort of like, if I think about it like this, like the law of total probability, right? Um, I'm basically saying like, okay, like, so if my probability on A and B is, some bit string, right? And and so like, probability of A, B, C, D being in some configuration is really like, I can read it as the probability of AB being in this configuration and CD being in this configuration. And now I have to multiply that out by what the value of that observable C is over AB and CD, right? But the observable on CD is trivial. It's just the identity, right? And so I can basically just multiply that. I can sort of like carry out that part of the sum over CD somewhat trivially, and I'm only left really with like the sum over AB.
Right.
Does that make sense?
No, no, yeah. I guess my concern is exactly when the entire force set of measurements would be non-commuting. I've got a specific non-locality kind of application in mind, which seems to be related to the framework as you're presenting it in terms of sampling. Maybe I'll kind of send it to you separately in an email.
Yeah. Okay. That sounds good. But yes, there's lots of ways in which that could break easily. And so if you have, if there is, um, let me just say that, like, if for whatever reason, you there's an observable which uh, there's a term in your Hamiltonian that depends on all four qubits, or uh, then of course you need the total distribution on all four of them. But my contention, I think, is that, like, in order to, you can basically compute the expectation value of any observable by looking at it term by term. And if you look at a single term of any particular expansion of the original observable, then just the expectation value of one term only involves the qubits that's involved in that term. That's it.
Right.
You don't need the distribution of bit strings over everything else in order to just compute the expectation value of this thing.
Right. Right. Thank you.
Yep. Well, thanks for the discussion. It's definitely gave me food for thought as well. Okay, so that's how readout errors go, and how we mitigate for readout errors. There's other ways, as I mentioned as well. Um, in PyQuil, for example, we do it in a slightly different way. We call it, well, this is one of the two methods that's in PyQuil. Another is using something called symmetrization and calibration. Maybe at some point in the future we could talk about that, but I thought for today we could just limit the discussion to something like this. Um, I finally wanted to also talk about gate errors. Um, so again, this is going to be like, a very quick, breezy walkthrough of what density operators are. Hopefully you all had a chance to by now look at, and discuss in some detail what density operators are. But I'll offer just sort of like a very quick review. Um, so essentially, when we talk about like basic quantum mechanics, and we talk about Schrodinger's equation and all that stuff, Schrodinger's equation is basically saying that if you take some initial quantum state psi, um, this is like what we call like a pure quantum state, right? Um, then, if your system has a particular Hamiltonian, and the Hamiltonian is really something that governs the dynamics of a system. Classically speaking, it's the energy of a system, right? It's like the kinetic energy of a system plus its potential energy. Um, and so if this is the Hamiltonian, then the Hamiltonian is a Hermitian observable. Um, and essentially we say that it generates these time translations, or it evolves your initial quantum state psi I according to this particular unitary matrix into some final quantum state. So this is oftentimes, in fact, like what people say. Um, you know, Folks who do quantum mechanics for a living, I guess, sometimes get annoyed by this public perception that, there's this quantum uncertainty. Well, yes, there's quantum uncertainty in observables, right? But the underlying quantum state is totally deterministically computed, right? Like, I mean, it's basically like, if you tell me what the initial wave function is, and you tell me what the Hamiltonian is, then one can compute, in principle, at the very least, what the exact final wave function should look like, right? It's just that there's some sampling probability associated and some uncertainty associated with whatever observable that you're going to measure in this state. That's what gives you things like the Heisenberg uncertainty principle, what have you, right? But otherwise, it's completely deterministic, right? the wave function is totally deterministic. But anyway, this is like the usual picture of quantum mechanics, right? Like where we have these pure quantum states and they evolve according to unitary matrices. In real life, things are not so ideal, and things are actually more appropriately uh, described by the so-called density operators passing through some noisy quantum channel. So let me try and unpack that a little bit. So first of all, we'll just take the example of a pure quantum state whose density operator is given as this outer product. So this is why we call it an operator in the first place, right? Because if you kind of like go back to your um, Brockett kind of dictionary or vocabulary. So this thing, a ket is a row vector. Oh, sorry, it's a column vector, and a bra is a row vector, right? So a column times a row vector should give you a matrix, right? And so a matrix is, in this representation, basically that's an operator, right? Because this could operate on some other quantum state, psi, say, and produce another quantum state. Uh, and that's why we call these things density operators and not density states, right? Because strictly speaking, in this particular Hilbert space, they act as operators. But nevertheless, like these are operators that really define, the state of some quantum system. And instead of, they don't necessarily have to evolve unitarily, although they could, like I could just as well represent the process that's happening here by saying that like rho, which is, this psi ket bra psi, this basically goes to something like u times psi times bra psi u dagger, right? And that will basically tell me what psi, what the density operator is for this final quantum state. But more generally, this rho can pass through some noisy quantum channel. That quantum channel basically means that it is, maybe like some unitary operation, but also plus some other noise, right? And that sort of thing is more generally described in a process like this. So where we have these operators, A's, AI dagger, sort of like sandwiching our density operator over here. And the constraint that they have is that, AI dagger AI has to, their total sum has to equal to the identity. So in the trivial case where this rho is passing through some non-noisy quantum channel, or in other words, it's just like evolving unitarily, then there is just a single I, and this AI is just this U. It's just some unitary operator, right? Um, so, that sort of goes back to the definition of what unitary operators are, right? So like if it's just like a single I, then I just have like A dagger A is the identity, and that's like, basically what a unitary operator is. It's like, it's an operator whose inverse is like its conjugate transpose, right? Okay, good. So this is how we represent noisy quantum channels. Um, and quantum states, so over here, I just described the evolution of a pure quantum state through some noisy channel. And you can see that like now this has sort of like become a sum, right? It's become a sum over some types of states. And that's actually not a coincidence. I mean, like more generally, when we describe quantum states, it's more appropriate to describe them as sort of statistical mixtures of pure quantum states. And so what I mean by that, so mathematically, all that means is that you can imagine a bunch of pure quantum states, um, and now you just have a mixture of them, right? So there could be like some weights over here at the front as well, which weighs like, how many, like what fraction of these states you have, et cetera. But really that's like, you basically, like I'm sort of neglecting, I'm being a little, um, um, maybe like a little sloppy over here, but I really should have like you should imagine some sort of like coefficient that like sort of like weighs what fraction of these states you have in your ensemble. But really this is just like not very different from, say, having a basket full of um, apples and oranges and pears and bananas and whatever fruit you could imagine, and you have like a classical mixture of such things, right? So a quantum state, of course, is some quantum superposition of bit strings or whatever quantum states you can imagine. But once you produce that quantum state, that's a quantum state, right? So now imagine that like you have a basket of several of these quantum states. Like you have like, 1/5 of one particular type of quantum state, and you have like 2/5 of another type of quantum state. Like these are your apples and oranges, and so forth, right? So a good way to see an example of this, I guess, is like the following thing, which is a classical bit, right? So I can represent a classical bit as this density operator. Uh, so this is basically saying that I have like a classical mixture of 0 and 1, right? Um, on the other hand, remember that you must have by now done some sort of an experiment like a quantum dice, right? And in that quantum dice experiment, you must have had like, you probably produced like a Hadamard state, which was like an equal superposition of 0 and 1. Um, and that 0 and 1, that's actually a pure quantum state, right? So that's a quantum superposition of 0 and 1, which is very different in nature from this classical superposition, or this classical combination, rather, of 0 and 1, right? Um, and because now, like, I mean, like we can just sort of like quickly do the math in our heads. Um, so this plus state, so it's this Hadamard state is often known as the plus state, and that's because the Hadamard state is like the +1 eigenstate of the X operator. Uh, so just a convention that people like to follow. But anyway, so if you expand this out, this is like 1/2, 1 over square root of 2 times 1 over square root of 2 just gives me a 1/2 factor over here. But then I have 0 plus 1 kets and 0 plus 1 bras. And so this 0 times 0 gives me a 0, 0, which is this state. 1 times a 1 gives me 1, 1, which is this state. So I have both of these projectors, but I also have these cross terms, right? So I have 0 times 1, and I also have 1 times 0, right? And so this, like if I represent in matrix form, this thing is purely diagonal, right? So this, like you could read these as like kind of like the rows and columns of a 2 by 2 matrix, right? So in 0th row, 0 column, you have a entry of 1/2. In the first row, first column, you have an entry of 1/2. Over here, you have like an entry of 1/2 on all 4 uh, points of your 2 by 2 matrix. But over here, for the case of a classical bit, your off-diagonal elements are just going to be 0, right? And so sometimes people use those off-diagonal elements to actually, uh, quantify and assess if what you've actually produced is a quantum state or not, right? That's a good way of testing quantumness of your state. Um, but okay, so that's I just wanted to point that out. Now, an important channel that people often investigate when it comes to analyzing, gate errors on quantum devices, or in other words, like like one of the prototype channels, noisy channels that people like to think about, is known as the depolarizing channel. So it works something like this, right? So you have some initial state rho, and it could be some pure quantum state, or it could be a mixture of pure quantum states. We're making no such assumptions, but it's some quantum state rho. And once it passes through this depolarizing channel with some probability p, it remains in its original state rho. And with remaining probability, it becomes this so-called totally mixed state. Okay, so what this totally mixed state is essentially, so you already saw an example of a totally mixed state. In the case of a single qubit, it is precisely this classical bit, right? Uh, and if you're familiar with the Bloch sphere, uh, so if you remember, like, I mean, the Bloch sphere, the different points on the surface of the Bloch sphere told us about the different possible single qubit states, right? Now, but those states on the surface of a Bloch sphere are actually pure single qubit states. Okay, that's a very important point, because actually, not all quantum states actually belong there, right? So there's lots and lots of quantum states that actually are somewhere inside the sphere. They're not on the surface. Okay, the only states that are on the surface are just the pure one qubit states. Um, and in fact, this totally mixed state is something that lives exactly at the origin. So you can see that, like, I mean, this projector 00 plus 1, this basically comes out to be the identity, right? Because this is just a diagonal matrix, right? And so, of course, there's exact analogs for this in higher dimensions. You have like 00, like the projector on the 00 state plus the projector on the 01 state plus the projector on the 10 state plus the projector on the 11 state. And that will equal the identity, and then there's a factor of 1/4 there to, account for the probabilities. And that's the totally mixed state in dimension 2, right? Um, so this depolarizing channel sort of, this is basically, uh, it's that's basically the statement that, like, with some probability you get this original state, and with remaining probability you produce this totally mixed state. And this, this, while not an immediately appropriate model of noise on physical QPUs, you can, quite readily in many ways sort of obtain this model. We do this all the time. We create this noisy channel all the time when we're sort of benchmarking our quantum devices in a process called randomized benchmarking. You'll get to learn a little bit about that next time when we talk about the quantum supremacy experiment. And as you'll learn in the quantum supremacy experiment, there too, this is the sort of like the appropriate noise channel to think about over there. But one very useful property um, about this depolarizing channel, and I invite you to sort of like, work this math out for yourself, um, is basically that the probability is exponential. And what I mean by that is the following, right? So like, let's say I have some original state rho, I pass it through a depolarizing channel. So I pass it once and it goes into this particular state. So now remember that this is also just some other rho, right? This is just like some other density matrix. Uh, let's call it rho prime, right? And that rho prime I can write out in terms of the original density matrix as in this particular form, right? Now I pass it through the depolarizing channel once more, and I'll get this particular thing. So the nice thing about this is that now, so this doesn't maybe immediately follow, but if you work out the math and you do some algebraic simplifications, you should be able to convince yourself that, like, yes, indeed. So now that I have, if I say, like, rho, if I replace rho with this expression again in this particular expression, then and you do some algebraic simplifications, you'll get that this is equal to p squared times rho plus 1 minus p squared times the totally mixed state. And then if you repeat this over and over again, you'll basically find you can prove by recursion, I guess, by induction, sorry, that this is eventually going to be p to the n times rho plus 1 minus p to the n times the totally mixed state. And so that property is something that we can use to perform gate error mitigation. And we can do that as follows. So the story goes like this, right? So when we have pure quantum states, we have these expectation values, right? So remember that these are the things that we are typically interested in calculating in, say, variational algorithms like QAOA and so forth. But really what we have access to in practice are these density operators, right? And in the density operator language, the way you compute expectation values is you take the trace of the density operator times whatever observable operator whose expectation value you're actually interested in. So this is the thing that you're actually going to be computing, if you have the state rho available to you. And rho could be, it could be a pure quantum state. If it's a pure quantum state, then it just reduces to that, right? But if it's some statistical mixture of pure quantum states, then it's going to be more generally just that number, right? But now let's compute what it looks like if I pass, like say, so if originally my rho was some pure state psi, right? For which the density matrix, remember, looks like ket psi bra psi, right? So this part is my original density matrix, right? Um, this is, of course, the observable whose expectation value I'm interested in. So basically, I'm saying, okay, I took this initial density matrix, psi psi, and I passed it through a depolarizing channel, and now I'm interested in computing the expectation value of this observable C. So taking this expression, I can compute what that expectation value is, right? So it's going to be P times the expectation value of that observable in the original state again, which is, uh, psi psi, plus 1 minus P times the expectation value of that observable in this totally mixed state, right? And so in that totally mixed state, basically, any operator times the identity is that operator again. So basically what I'm taking is the trace of that operator. Now that operator, it turns out, if it's an operator over qubits, then I can always express this as some linear combination of Pauli operators. Um, and the nice thing about Pauli operators is that their trace vanishes. Okay, they are traceless matrices. And so, an example of so you've seen example of such Pauli operator sums, like, when we did the max cut problem in QAOA last time, like you had the Hamiltonian that looked like Z1, Z2 plus Z2, Z3, etc. Right? So those are all traceless terms, basically. Like each of these terms, like if you take the trace of, like if you compute what they look like as matrices, and then you took the trace of those things, then they will come out to be zero, right? So that's a very nice property, right? Because this whole term just basically drops out, and all I'm left with is just P times the trace of this original pure density matrix times the observable whose expectation value I'm interested in, right? And so this thing, you can sort of quickly compute that it turns out to be just your original expectation value, the thing that you're actually interested in. Times now you have this like pesky little p sitting up front, right? So if we don't know what this p is, um, but we do have access to the left-hand side. Remember, so experimentally, this is what we're measuring, right? But our quantum device has some erroneous gates, and it produces, say, a depolarizing channel. And so we don't know what those errors are like, right? But like we know that, like, okay, this whatever value we're actually measuring is off by the true value by some amount, right? If it is a depolarizing channel, then this is actually a very nice property that we can exploit. Okay, so let's see how we can exploit it. Let's consider, so the broad idea here is what's known as digital zero noise extrapolation. And I can send you all some papers as well, as kind of further reading. Um, this has become a very popular method of sort of extrapolating or mitigating for gate errors in kind of the near term, for these near term algorithms. Like, of course, now when we talk about fault tolerant error corrected quantum computers, we're not talking about this type of error mitigation. We're talking about, error correction is a whole new sort of like topic in itself, um, where we're talking about like where we're using physical qubits to build logical qubits and so forth. We're not doing any of that, right? This is a very simple-minded thing we're doing, and it's assuming, let's say, like in this case, of course, like people have now worked out um, ways in which you could sort of relax the assumptions, but our assumption is going to be that we have some depolarizing noise channel, such as the one that I just presented on the previous slides, and that the idea is very simple. The idea is that we'll basically exaggerate the noise in the system artificially, right? Um, so we'll exaggerate the noise, and then we'll record what the expectation value looks like at that value of the noise parameter. And once we do this for several values of the noise parameters, we can then sort of work our way or infer our way backwards and say, like, okay, if this is what the value looks like at very large, uh, you know, values of the noise parameter, then maybe I can sort of like, infer what it looks like for very low values of the noise parameter. And so extrapolate to the zero noise limit. Okay. And so the reason why I picked the depolarizing channel is because, it's a sort of like fairly simple way to look at how this works. So let's take the example of the pure Bell state, right? So if you recall, the pure Bell state, it could be produced by a circuit that looks like this. Basically, first I produce like the quantum dice, right? Like 1 over square root 2, 0 plus 1. And then I'll just basically perform a C naught operation, which will basically put my 2-qubit state into this particular state, 0, 0 plus 1, 1. And now what I'm interested in is, this particular expectation value where I haven't specified C, right? All I know is that C is some Pauli observable. Um, and so of course, I mean, so I'm going to deliberately write it like this. I'm basically saying this expectation value is P to the 0 times, psi sandwich, C sandwich between the psi. Because of course, like any real number raised to the power 0 is equal to 1, right? But maybe this will make sense in just a bit, because if you think about it, as we just argued, if I run this particular circuit, I'm going to get P to the 1 times this expectation value, right? That's because I'm assuming that I'm passing through basically the circuit produces some ideal quantum state psi, and then afterwards, there's some depolarizing channel that happens after the 2-qubit gate. So okay, so maybe I need to say a word or two about that. So essentially, when people do this kind of noise modeling or noise mitigation, a typical assumption that also goes into all of this is that single qubit gates are practically noiseless. Okay, and that's a good assumption to make because we can basically make single qubit gate fidelities very, very high. The real challenge in making errors minimal on quantum devices is how good or not your 2-qubit gates are. Okay, so if you can produce very good 2-qubit gates, then you have a very good quantum computer, and if these fidelities are pretty bad, then your quantum device is pretty bad. But basically, the entire game is around how well or not your 2-qubit gates function. And so one useful way to model errors is like you say, like, okay, your 2-qubit gate is going to perform its ideal operation, in this case, a C naught operation. And then as soon as you see a 2-qubit gate, you can immediately follow that with the quantum channel, right? So in the language of what we discussed over here, um, basically rho is the ideal Bell state that is produced at the end of the H and the C naught. Um, and then because I just passed a C naught gate, and that C naught gate is noisy and imperfect, I'm going to pass my quantum state at the end of the C naught through this depolarizing channel. That's basically the idea, right? So this state psi psi is the pure Bell state, and rho basically evolves from this psi psi to psi psi with some probability p plus 1 minus p times the totally mixed state. So that's kind of the mental picture of what's happening here. So if that's what's going on, then if I measure out these qubits and estimate the expectation value, then I should get that the expectation value that I actually measure is going to be this erroneous probability, or rather, like the probability of measuring the original state times the original expectation value. But now here's the trick I can do, right? So like I can note the following, right? So C naught um, is just like any other quantum gate. It's a unitary operation, right? Um, so what is the inverse of C naught, right? Like, I mean, if U equals C naught, then what is U dagger? Well, it's actually C naught again, right? So what I can do is I can basically say, and I know that the way unitary operators work is like U dagger U is an identity, right? So basically I can insert an identity anywhere in my circuit, and logically, it will still be the same circuit, right? And so because the inverse of C naught is C naught again, what that means is that basically I can insert an identity in the form of two C naughts, one after the other, no gates in between, right? This operation, logically speaking, um, is is just an identity operation, right? But what it does, because but if I actually carry it out on a physical QPU, on a physical device, this is actually a noisy operation, right? And so because this is a noisy operation, every time I get some ideal quantum state at this point, I'm going to have to pass it through some depolarizing channel, right? And so let's say, like, I produce an ideal Bell state over here. I pass it through some depolarizing channel. Good. Now I have some rho. Now I pass it again through some C naught. Okay, good. The C naught just evolves it unitarily, ideally. But after that, I evolve it according to some noisy channel, right? At that point, I have now like P squared times the original rho plus 1 minus P squared times the totally mixed state. And then finally, if I pass it through a third C naught and do this again, now I have like a total of, P cubed times the original expectation value. That's what the expectation value I will actually observe from this setup, right? And likewise, I can do this again. I can insert an identity over here, and I can insert another identity over here, right? And so now I have p to the 5 times the original expectation value. I can only do this for an odd number of like power, right? So like if I cannot really do this for say p squared. Why? Because if I just have like two C naughts over here, then that's a C naught times a C naught, which is just the identity, and in that case, I only have a Hadamard left. In which case, I don't have the same logical circuit again. What I'm interested in doing is preserving the same original logical circuit, but exaggerating the noise in the physical realization of that circuit, right? Um, and so the advantage of doing that sort of like noise exaggeration is as follows, right? So remember that what I'm interested in solving for is this original expectation value, C sandwiched between the sides, right? And I wrote it deliberately in this form as p to the 0 times the sandwich, because p to the 0 is just 1, right? But now, so here's the data that I've managed to collect, right? So I've said like, okay, I have p to the 1, p raised to the power 1 times this expectation value, p raised to the power 3 times this expectation value, etc., right? So this basically looks like, something. So what I'm observing is, let's call that y, right? So y is what I observe, right? This is like the thing that I can experimentally have access to. C is the thing that I'm actually trying to solve for, right? That's like this particular sandwich over here. Uh, P is some unknown probability, right? Like, I mean, like, I don't really know what that probability is, but N is something that I am controlling myself, right? By introducing more and more C naught gates, right? So in this case, N is 1. In this case, N is 3. In this case, N is 5, etc. So I get a whole bunch of points, right, for various values of N. Uh, for various values of N, I will also correspondingly experimentally determine what my different y's were, right? Uh, and so, this is sort of like an exponential equation, right? So now if I take logs on both sides, this is log of y equals log of this whole thing. And I can break apart the logarithm of this whole thing as, n times log of p plus log of c, right? That's just the equation of a straight line, right? So like, I mean, if I imagine that log of y is my y-axis and log of p is my x-axis, then n is simply uh, the slope and log of c is simply the y-intercept, right? So because p is a probability, log of p will typically be some negative number, right? So this will actually be, and of course are integers like this, right? Like 1, 3, 5, etc. Um, so these will, this will be sort of like a downward sloping graph, straight line graph, right? Hopefully. Um, and then the idea is that, like, you plot this stuff on a straight line, and you sort of like, like you, so, you'll get, you are controlling what n is. You will experimentally determine what y is, right? Like, so plot the log of y against n, right, on some graph paper, um, and then try and like extrapolate back to what happens at n equals 0. Remember that n equals 0 is the value that you're actually interested in, right? And at n equals 0, basically you'll just get the y-intercept, which is log of c. And so if you look at log of c and then take its exponential, you should be able to work out what the true ideal expectation value is. And so that's what we mean by saying like, okay, let's exaggerate the noise parameter artificially. Uh, that's what we did over here, right? Recording the expectation value each time. That's basically what we, that's the total product that we can compute or that we can actually observe. And once we have that, then we can sort of use this kind of trick to extrapolate back to the zero noise limit and infer what the ideal expectation value should be like. So that's basically the trick. I won't give away too much more. Basically describe the math, but I'll let you try your hand at how to like actually code this up and actually make it work in practice. Um, but before we move on to the exercises, I wanted to see if there were any questions about gate errors or anything else.
Does a similar trick work out when we try different other channels?
Yeah, so there's one of the way that this usually works is that you need to have some sort of a uh, stochastic channel. So some channel that sort of looks like something like this, and so there are ways to sort of turn other channels into stochastic channels. Um, and once you have done that, so there's sort of like this pre-step where you turn some other channel into something that looks like a depolarizing channel. And once you have a depolarizing channel, then you can carry out this kind of thing. Um, so when we do, for example, randomized benchmarking, right? Um, in randomized benchmarking, you sort of sandwich your gate with these Clifford elements. And once you do this many times, your Clifford elements essentially produce a depolarizing channel on average. And so that, that lets you, like, the nice thing about the depolarizing channel is like it's symmetry, right? Like, I mean, because like, nice properties like things like terms dropping out and the expectation value scaling according to some real number which you can identify as a probability. Those are things that you don't typically find with other channels. And so a useful strategy is like to first convert um, a channel into something that looks like a depolarizing channel. That's a useful strategy that people often typically follow, and that's sort of like does go back to the days of even randomized benchmarking, which is one of the earliest successful sort of benchmarking techniques. Uh, but also more, like, I mean, people also, and I could point you to a paper on this, but uh, people also sort of like think about like, okay, what if you did not do any of that, right? Like, what if, for example, you just had some channel and you just exaggerated the noise, right? Like, I mean, okay, like, sure, I'm not going to assume that this is a depolarizing channel. But what I am going to do is I'm just going to exaggerate the noise in such a way that it keeps the same um, logical structure, that it produces the same logical circuit, but nevertheless, like, just exaggerates the noise at a physical level without me necessarily assuming anything about what the channel looks like. So in that case, you're not necessarily guaranteed that your data is going to fit like this. But what you can try, right, which is, I guess, fair game, is you say, well, it's some function, right? Like, I don't know what function it is, but like, I mean, okay, it's like some function on the left-hand side, like, some, like, you can imagine, like, I mean, like that I'm not, like, right now I could like work out a few properties about the depolarizing channel and sort of like exactly work out that if I put everything on the logarithm scale, then this looks like the equation of a straight line, right? But like if I knew nothing about my channel or the noise properties, then I could just start off with like some original function and say like, okay, like maybe it's some polynomial fit, you know, to n, or maybe it's an exponential fit in this case, or maybe it's a linear fit, or maybe I don't know what fit it is. Like I'm just going to try a few fits, according to some loss function, say. Um, and maybe we'll see, like, I mean, like one of them, like really, one of those fits really explains the data really well. And if it does, then I'll just like fit that trend line and extrapolate back to zero. And there's been, I think, like, I mean, I'm not aware of like extensive studies on this. Like one of the things that we were interested in is seeing if this might work for QAOA, this technique that I just explained. This is relatively new, by the way, but like we don't know if it works or not for QAOA. Maybe it does, maybe it doesn't. Uh, but it's certainly something to try. Like I think that's like sort of one of those open researchy level questions for sure.
Thank you. Anything?
Okay, we can move on to the tutorial over here. And I say tutorial because I really wanted to, like, I mean, just uh, basically let you all get your hands dirty with most of the stuff, but just to sort of like get you pushed in the right direction. Let me see why this isn't working. Give me 1 second, please. Okay. Still confused. Okay. Let's see. My computer is a mess. Okay. There we go. Okay. So the last time we used the wave function simulator, this time we will primarily use, what we call in-house a quantum computer object. And so, in your previous QAOA tutorial notebook, you must have seen something like this, the wave function simulator. Now I'm basically just saying, like, I'm going to get like a 2-qubit QVM. Okay, like, I mean, so you all should definitely play around with this and see, the largest number of qubits that your laptop can maybe uh, simulate reasonably. But going up to something like 10-ish qubits is usually fine, for example. Anything more than that starts to get a little bit tricky on, say, a standard laptop at the very least. But anyway, just let's play with qubits 0 and 1 for now. So very simple thing we're going to do, first of all, just compute what the expectation value of the observable Z is in a fair quantum dice, the Hadamard state. Many of you have probably done something like this before, but just as kind of like a nice warm-up. So remember how we were computing expectation values last time, right? Like we simply used the wave function simulator, and we used its expectation method, in which we like basically prescribed what the program was that prepared the quantum state in which we wanted to compute the expectation value. And then we also defined what the observable was that that we actually wanted to measure in that state. And so here it's just as the observable. And so in this particular state, it should just come out to be 0. Now, if we talked about how, like, I mean, in real life, we, of course, because quantum devices are probabilistic machines, we have to estimate it via sampling. And so, let's sample it via some shots, right? Let's say 1,000 shots, right? So like now I'm basically initiating my program. I have to declare a readout register, right? So this is what, RO just stands for readout. And I carry out the Hadamard gate on qubit 0. And this is basically just saying that, like, measure out qubit 0 and place it on the 0th part of this readout array RO. Okay, that's all it's saying. And then rapid num shots loop is just a wrapper that basically says, okay, this program should be carried out a total of 1,000 shots, essentially. Um, and so now basically I just compile it to my quantum computer uh, and produce an executable. And I will now just generate some samples. So the shape, so the samples basically is just a NumPy array. It's like the number of shots. Its shape looks like the number of shots. That's how many rows you have. And the columns are basically the number of qubits that you're measuring. So in this case, because it's a quantum dice, you would roughly expect like about half ones and about half zeros, right? So good, like this is like what the first 5 shots looks like. Um, so now we're going to estimate the expectation value of Z using these shots, right? And we're going to make use of the fact that Z on the 0 state takes on the value 1, and Z on the 1 state takes on the value -1, right? And so remember that, on my quantum device, all I am able to really register is just that this is a 0 and this is a 1, right? Um, so basically, I need a way to map, like, I mean, if I'm computing this particular number, right? Or sorry, this particular variable or observable, then I know that this takes on the value 1 on 0, on the bit 0, and it takes on the value -1 on the value 1. So a quick and simple way of mapping like this, huge array of ones and zeros into an array of -1s and ones respectively is to just say 1 minus 2 times, this entire array. So like when I do, like in NumPy, the nice thing about NumPy is that if samples is like a NumPy array, then this will basically carry out, this particular operation on each element of that NumPy array, right? So for example, it will turn like this first thing into 1 minus 2 times this number, 1 minus 2 times this number, 1 minus 2 times this number, etc. Right? So 1 minus 2 times 1 gives me a -1, right? And 1 minus 2 times 0 gives me a 1, which is exactly the transformation that I needed. So this basically just transforms my samples into a sample of the values or eigenvalues of the Z operator, right? And so now that I know what the value this observable takes on each of those samples, and I have like 1,000, a record of 1,000 such samples, I can basically just compute the mean of those things, and that's my expectation value. And wow, like I mean that really came out to be exactly 0. I wasn't really expecting that, so let's see if that comes out to be again. Okay, good. There's some variance. Uh, wow, that was pretty lucky. But anyway, this was, in practice, you'll often see something that's like close to 0, though not exactly equal, right, to our ideal value. And so now, like, let's, if you recall what we were saying about performing, um, like if we wanted to, like, say we performed several of such experiments above, right? So like this is just one experiment in which we ran the quantum circuit for a total of 1,000 times, and we obtained some value, and it came out to be this particular value, -0.032, right? Um, but if we really wanted to get like, good statistics on this and say, okay, like, what, like maybe there's some variance around, our estimation of the expected value. Uh, let's actually perform several of these experiments, right? And compute, like say the distribution of all these averages, right? So each run is really like a run over 1,000 shots, right? And I'm going to basically perform 1,000 such experiments or 1,000 such runs, right? So basically that's what I'm doing over here. Um, so in each run, I collect samples. I transform those samples to Z eigenvalues. I compute the mean of those Z eigenvalues, and I collect that mean. And now basically I'm just going to plot a histogram of what those Z eigenvalues looks like. And this should finish momentarily. And we should see something that looks like a bell-shaped curve, right? So like, I mean, we know we computed that the ideal expectation value should be centered around, is in fact equal to 0. So in a typical experiment, um, and by an experiment, I mean, I run the quantum circuit for 1,000 shots. So in a typical experiment of 1,000 shots, if I, collect bit strings and I compute the expectation value, I should get some value that's quite close to 0.00, right? But in some stray cases, I will get something that's actually around zero point 0.1 or maybe around negative zero point 0.1 and so forth, right? That's kind of like the picture that this thing is painting over here. Now we can also estimate expectation values of other observables, right? Like we're not limited to Z. We can also measure X and Y, but in order to do so, we do need to rotate into the appropriate basis, since our quantum computer can really only measure in the Z basis. Remember that, when we say we're measuring in some basis, when I say we're measuring in the Z basis, I mean the basis in which Z is diagonal. And this is like a convention that quantum people have just chosen, that, our 0 and 1 are eigenstates of the Z observable, right? And so this is what we call the computational basis, right? In which like we've defined our zeros and ones in such a way that diagonalizes Z, but remember that neither X nor Y are diagonal, right? So they are not, those are something, in order to diagonalize them, we need to rotate into another basis. And so the way to do that is you note that like, if you wanted to measure X, then you can sort of work out that, if you sandwich a Z with a Hadamard gate on both sides, that gives you an X, right? So in other words, if you wanted to calculate the expectation value of X in some state psi, which is again, just a sandwich of X between in the psi state, then basically using this identity, which this is just matrix multiplication, which you can work out and convince yourself that this is true. Um, Another way to think about it, by the way, is that if you, in the block sphere picture, right, like you start off with, let me actually show you the block sphere. I had it here somewhere. Yes. So the block sphere, like this is the 0 state, right? Like now if you apply a Hadamard gate, it brings you to this state, the state that is pointing towards the positive x-axis. So because it's pointing to the positive x-axis, it becomes kind of like the 0 of the x operator, right? 0 is the 0 of the Z operator because it's pointing along the positive Z direction. And 1 is like the negative 1 eigenstate of the Z operator because it's pointing along the negative Z direction along the Z axis. So likewise, this is like the positive. So if I just transform 0 to the +1 eigenstate of X operator, that's basically what the Hadamard gate is doing. And also you can just carry out this matrix multiplication and convince yourself that this is true. And so basically what that means is that like, now I'm taking, if you think about it, like this expression is saying like you should just compute Z, which is what we ultimately always do, by the way, on a quantum device, right? Uh, you're computing Z in the state given by H times psi, right? So what that means is that if you want to measure X, or the expectation value of X, in some state psi, doesn't matter what that state is, all you have to do is before measuring out, your qubits, just place H on the qubits over which you want to, compute this observable X. That's pretty much it, right? So that's all that this is saying. And then we carry out the usual procedure, right? So our program here is, well, it's again the quantum dice experiment. And in that particular case, now, as I just mentioned, like, the Hadamard transforms the 0 state, or the starting state, to the +1 eigenstate of the X operator. Naturally, the expectation value of the X operator is just going to come out to be plus 1.0, right? Which is what this is saying. And we can estimate the same thing via sampling, right? So uh, let us first apply this Hadamard gate. Now, the thing is, because we're going to be measuring in the X basis, And because we just argued that in order to measure in the x basis, we have to apply this Hadamard before measuring. So basically, this is just applying another Hadamard to perform in the x basis, right? So this Hadamard just basically cancels out that Hadamard, and so all you're left with is just a zero state again. So this is actually trivial, but more generally, you can imagine that you could replace this part by some other random stuff. Like this could be like ry some random angle on zero followed by rz of some random angle on zero, and then to measure the x expectation value in that state, you would still do this part, right? And then you would just measure, and you would basically do the same thing as you did before. Basically, you're now measuring z really, but because you performed that rotation, I'm calling it x sides, right? But really, it's like you're pretending like a z all over again, and you're transforming the zeros to ones and the ones to minus ones, and you're computing the average of those things. And now, because it's like you only just had the zero state, right? There's basically no variance. Your averages, your samples, the bits that you read out are always just zero and nothing else. Um, so you just get this thing and nothing else, right? Then there's no variance around this whatsoever, which is pretty nice. But again, only true on an ideal device, of course. Uh, and likewise, if you wanted to measure the y-axis, or sorry, the y-observable, here's one way to do this. You note that u dagger u, if you take u to be rx minus pi over 2, then you can sort of work out that u dagger z times u equals minus 1. Okay. And again, y rx minus pi over 2, you can sort of go back to your block sphere picture. And, if so, rx is basically a rotation about the x-axis of this much angle, right? So if I'm starting off in the zero state, then I have to sort of like counterclockwise rotate zero by 90 degrees or pi over 2 radians to make it point along the positive y-axis. Okay, uh, that's good enough for states, and you can argue, you can sort of like work out that if you apply u to zero, where u is this particular operation, then the resultant state is going to be indeed a positive, uh, a plus one eigenstate of the y operator. Um, but unitary operators are more than just states, right? They also have some additional information, and in this case, it turns out that there is an overall factor of a minus sign difference. So there is an overall phase difference involved over here, which you have to account for. But basically, that's simple to take care of, right? So like, I mean, the idea is roughly the same. We can just apply an Rx minus pi over 2 before measuring, and then we carry out the usual procedure. But we just need to take care of the special minus sign over here. That's the only difference. Um, so I do that. I get the expectation value, uh, equal to 0 in this case, right? Um, that's what I calculate from like using the wave function simulator. And as before, or as I just explained, like, I mean, like we will first carry out the usual program, but then before measuring, we will rotate it to this so-called y basis. Um, and, this is what our compiled program looks like. And as before, I will now just run it over several number of experiments, taking care of that minus sign. Um, and what I should again see is some distribution, like some bell-shaped distribution that's centered around 0. And, indeed, um, this kind of throws it off a little bit, but basically, I hopefully this is convincing enough that indeed there is a bell-shaped curve and it is centered around 0, right? Okay, good. So now let's see what happens if we introduce some readout error on our qubits, right? So if you want, you can read a little bit more about what the API looks like over here. This is the entire API reference, by the way. But basically, like, it's very simple to define uncorrelated readout errors. on our qubits if you want to simulate this kind of readout noise. Basically, the idea is that like, you specify what the qubit is, and P00 is the probability of obtaining the measurement result 0, given that the qubit is in the state 0. So this is like, if you read out the qubit into state 0, given that it was sampled as a 0. And likewise, P11 is the probability um, of, that you read out the bit being in the state 1, given that it was actually also sampled to be in the state 1. So that's all it's saying. And in general, like, of course, those two things don't have to be the same. Remember that, once I've specified P00, then I know what P10 is, right? Because of the way that probabilities work, right? Like, I mean, uh, P1 of 0 is like, probability of reading 1 given that it was actually sampled to be 0. And that has to be 1 minus this probability, right? Um, and likewise, P0 given 1 is also completely specified once I've specified this probability, right? So that's the probability that if I actually sampled 1 but then read it out as 1, right? Um, that has to be 1 minus the probability that I actually sampled 1, but then read it out as a 0. Okay, so once I specify these two probabilities, then I specify the other two probabilities automatically. Uh, but, I should say that more generally speaking, what one should think about and what one has to in practice sort of mitigate for uh, are the more complicated probabilities that one might encounter, uh, that I guess like could be described by that giant, where to go, yeah, sorry, is that the yeah, there we go. So more generally speaking, right, like we shouldn't just be specifying P0 given 0, but rather like what these ginormous probabilities are. Now, of course, it's true that once you define like what these probabilities are, this is in turn going to have an impact on what all of these probabilities are, right? But generally speaking, on our physical QPUs, uh, it like these kind of probabilities don't break apart nicely on a per qubit basis. They actually, I mean, you can compute what these things are on a per qubit basis. Uh, these are perfectly fine numbers to compute, but also like, by introducing the noise model like this, you're sort of assuming that each qubit has its own kind of uncorrelated readout noise, which isn't necessarily true. That's the only point I'm trying to drive home here. But anyway, this is at least one simple way of defining noisy readout, right? And so you define this noisy readout, and you apply this Hadamard gate, and you measure it. So basically, we're still applying the same. We're still using the same program and everything, but we're just introducing some readout noise. And let's see what how that changes um, the expectation value of the Z observable. So, basically the idea is that like, even though before, like, I mean, let's go back to the circuit for just a bit and see that like, I mean, oh, well, okay, it's just like the Hadamard, 0+1 state. So maybe we can just work it out in our heads, like, that it's like, because, it's like 1/2 times 1 plus 1/2 times, like, I mean, -1, it's just going to be 0, of course. But now, there's some probability that like every time you read a 0, you can actually flip it out to be a 1 and vice versa. That number has sort of shifted, uh, looks like more in favor of the -1, so more in favor of like, ones being read out. So presumably because of readout noise, like, in our setup, like there are more ones being read out here than there are zeros, which is why uh, you see a sort of like shift towards the left in this case. Okay, so that's one way in which readout errors can sort of like skew your readings, right? So at this point, like I wanted to introduce, just to sort of suggest some exercises. Of course, like this tutorial just like showed you um, some steps to sort of work through for just a simple quantum dice experiment, but you should repeat the above analysis for the Bell state. That's like the simplest kind of 2-qubit circuit that you can imagine, I guess. And what I think you should try and do is to measure the observable ZZ, XX, and then also like a hybrid of those two, right? Like, I mean, so ZZ should be simple, right? Because you're not really doing any pre-rotations or anything like that. The one complication that can come up, which I'll mention over here, is that, like, whereas previously you just had like a single Z or a single array of, let's scroll up all the way over here, right? So like you had like a simple sort of like one-dimensional array of values. Now you have like, your NumPy array is going to be like 1,000 or n shots, comma, 2 shaped uh, array, right? And so in order to measure ZZ, what you have to do is you have to multiply on a row by row basis this element times the next element, plus this element times the next element, plus this, plus the product. Like you first have to compute what the products are on a row by row basis, add those products up, and then divide them. A common mistake that people make over here is that they will take the average of this column and then multiply that by the average of that column. That's not the right way of going about it at all, right? Because if you do it like that, uh, well, you should definitely try it. But like, I mean, there's one correct answer for ZZ in the Bell state, and that is equal to 1, right? Like, I mean, like you should basically always get, whether you're in 0, 0 or the 1, 1 state, you will always find um, that you get the value, of this operator being equal to 1. However, if you do it the other way, in which you compute like, the average of the first column times the average of the second column, then you'll find it to be 0, right? So drastically different results. And so you have to be careful. And so secondly, this is, again, like we just argued, it's like measuring ZZ, except you have to do these types of pre-rotations on both of the qubits. And with XZ, you only have to do pre-rotation on one of the qubits. So this should be like a nice exercise in getting comfortable with pre-rotations. So you should do them exactly first, just to sort of convince yourself, like using the wave function simulator or using pen and paper if you're more comfortable with that. Just to, like, so you know exactly what the answer is that you should expect. Then you should do it via sampling. And then I would say, like, investigate the dependence of the standard error on the number of shots. So the standard error is fortunately something that you can just, it's a standard thing that you can just compute in NumPy, right? So if you have, and again, like an array like this, you can, there's like a numpy.standard error or like std_error or something like that, or even like a variance, right? Like, I mean, you can compute the variance of this particular thing. Well, that will give you the variance of this particular sample. But like, I mean, if you compute, for example, if you do an experiment like this, where you had like several of these expectation values, and you computed the variance over this particular collection of expectation values, that should give you the standard error of the mean. And then, that will tell you how thick or thin this particular bell-shaped curve is. And you should explore what the dependence of, like, how many shots do you need, say, to estimate this to, say, like 3 decimal places, or like, to a precision in which you're basically sure that it's not going to be that the error is not going to be any more significant than 0.01, for example. And how many shots do you need so that your estimate is accurate to 0.0001 or something like that, right? So try to, like, I mean, try to work out by hand, based on the expression that we discussed earlier in the slides, what that number of shots should be, and then, actually try to empirically see what that is. That would be sort of like a good exercise. And next, I would say, like, introduce some readout error on both of the qubits. You can use these values that I just like used here, or you can cook up some of your own. I would say, like, I mean, try everything. And investigate how the expectation values have shifted, right? And then perform the readout error mitigation as we had explained in the slides. This is going to be non-trivial, that's right? So I don't want to give away too much of this. I basically just wanted to tell you how to define a noisy readout. And then we sort of verbally discussed how we would do this. So remember, I'll remind you again that basically this part, the left-hand side, this left-hand side column, this is something that we get from the quantum circuit itself, right? We then have to estimate this confusion matrix, and this confusion matrix is something that we do not obtain using this program. It's something that we have to, we still need to specify these noisy probabilities. So this part, basically this line will still be part of whatever program you write, right? But you basically have to write two to the n different programs, one for each of the possible starting bit strings, right? So, and depending on whether there's a one in the starting, qubit or not, you're going to place an X on that qubit or not, right? So for example, in this particular state, like you would measure, you would basically just, not apply anything to any of the qubits. When this is your starting state, then you would apply X gate to all of the qubits. And then you would measure it out, and then you would count the fraction of times you saw 000, and you would count the fraction of times you saw 001, and you would count the fraction of times you saw 010, et cetera, right? So that's a whole bunch of experiments that you need to compute that will allow you to compute what this confusion matrix is. This is something you compute from the, again, the quantum circuit itself, which is this thing. And yeah, that's it. Like once you have that confusion matrix, then you can sort of invert that confusion matrix, multiply the inverse from the left onto this column vector on the left-hand side, and that gives you the true sampling probabilities. Once you have the sampling probabilities, then you can sort of go back to this particular thingy over here, and this expression will let you figure out what the true expectation value should have been like. So I guess, try to get your hands dirty with that. I will, of course, send you all some solutions. And I also wanted to include an exercise here on gate error mitigation. Unfortunately, something broke either in my setup or there's maybe like a bug in Pipewheel. I will try to figure that out soon. If I can't do that tonight, then definitely before the end of the lecture series. But I will send out an exercise on gate error mitigation as well. So hopefully you all should have gotten a copy of this notebook. And yeah, I mean, I guess I'll take any questions if there are any.
Questions? None? Everything's good. Okay.
Cool. Okay. Cool. All right. Well, I would say, I would suggest, like, I guess we have half an hour remaining. So, I'll be around for a bit more. I might take like a 5-10 minute break and come back. But I guess in the meantime, just, get started, make sure you can run this code and see if you can get started on the exercises. I will try to mail in solutions tonight as well. But strong recommendation to not sort of, jump straight to the solutions. I think like, this part is like, the reason why I left it deliberately for you all to do is because like there's very little actual, okay, there's Pikewill, but there's very little new Pikewill to do. It's like, it's all like, if you know the syntax, if you can write a code like this and you can do some basic NumPy stuff, then, this is really an exercise of exactly what we just discussed in the slides and translating that to code. So I think this is a nice exercise to do. And this is sort of like more of a warm-up exercise. So yeah, why don't you all get started in the meantime? And, let me know if you run into any problems running Pikewill or anything like that.
Sounds good.
Cool. I'll be back in a few minutes.
So there were a couple of questions from students from the first exercise, I think.
Okay. Maybe we can go over them.
Anyone?
The question is related to performance ratio from the last notebook. So between the fully connected and the ring topology, performance ratio is not varying. It's always 0.98. So that's a problem.
I'm sorry, I couldn't completely catch the question. You said the performance ratio was not varying for which problem?
For both the first and second problem, the ring topology and the fully connected problem.
So I'll have to remind myself. Let me stop sharing my. Am I still sharing my? Oh, hang on. Okay. I'll have to bring out my. You said the first two problems.
Yes.
So for ring topology, okay. Well, there's definitely a solution for the ring topology, uh, for sure, that you should get, and I think that was even in the solution guide. I might have left the completely connected graph as a further exercise, but should be one. Gerard, did you get a chance to send them the solution guide for the first exercise? Or well, I mean, I don't know if like the students are allowed to see the solution guide or how this works, but uh, for the ring topology, let me actually post the paper over here. There's a well-known result um, that says I think it's something like if you have like an n-qubit ring Hamiltonian for the max cut problem, then you need p equals n over 2, I believe, steps in order to completely solve or to produce a state that will basically optimally solve the max cut problem. And that is somewhere in this particular paper. Let me see how I can do in the chat. Okay. I'm just posting it on the chat board. Okay. So that answers that one. So for the fully connected, I think there's some uh, partial answers known. Generically speaking, like, I mean, the performance should increase as a function of P. If it's not increasing, I would say there's probably some bug that you should look into. But like how actually, like, I mean, that thing scales as a function of n, I don't know that off the top of my head, and I'm not sure if there's like actually well-known results around that either. Like certainly, like, I mean, what's known is that like, I mean, for you definitely need um, there's sort of like some results known around, like, okay, like, I mean, this is how many steps you need in order for the QAOA algorithm to actually talk to the entire graph in the first place. Uh, but that's sort of like, I mean, like that's maybe that's actually like works less for a completely connected graph now that I think about it. But yeah, I mean, like long story cut short, I don't think there's a nice result like the one that I just posted uh, for fully connected graphs, as far as I'm aware. But nevertheless, like it is generally true that uh, it should increase. Now you're saying that, like, I mean, it's if it's plateauing, that might be a different thing. Like, I mean, if it's increasing and then like you don't see like much of a general increase, that's something that like I think like a few authors pointed out could be the case, maybe. Um, but if you found something like that, that would be very interesting, and maybe uh, you should explore that a bit more, and I'd be curious to see the results of that too. But if you simply like don't see an increase in performance going from say p equals 1 to p equals 2, then there's probably something wrong.
We focus on p equals to 1 only for 40 cases.
For 4 qubits?
Five.
Okay. So the exercise says, right, how does this compare to, yes, how does, okay, yeah. So the second exercise is basically just asking you to compare how, like, I mean, so how does, like, I mean, so actually, like, this is a question I didn't really know off the top of my head. But I'm curious, like, what did you find? Like, I mean, so for p equals 1 QAOA, if you have, like, say, a fully connected graph, right? And you computed the approximation ratio for the fully connected graph, right? Like you can separately compute what the, say, the maximum eigenvalue is, right? Or the optimal eigenvalue is, and then you compute it, like, I mean, um, what the value is under QAOA. I forget if we were looking at the maximum or the minimum. I guess we were looking at the minimum. Sorry. So if you compute the minimum eigenvalue, and then using QAOA you find what the minimum uh, expectation value you could reach for that observable, right? How did the two compare for the linear chain versus the fully connected one? Like how did the approximation performance ratios differ?
They are the same.
The fully connected one had a better performance ratio.
The fully connected had the better one? Okay, good. Yes, that's intuitively what I would expect as well. Uh, the reason why that should happen is as follows, right? So uh, when you think about what QAOA is doing, it's saying like, okay, let me exponentiate uh, the Hamiltonian, right? When I exponentiate the Hamiltonian is a sum of ZZ terms, right? One for each edge. So now if I have, say, like, I mean, if imagine 4 qubits, so you had 4 qubits in your problem, right? And if I have a linear chain, right, on my first, if I only have p equals 1 QOA, then I have this edge, I have this edge, and I have this edge, right? So if I'm looking at, say, qubit 1 over here, when I exponentiate it, it's only doing e to the I gamma z1, z2, right? And it's doing e to the I gamma z2, z3, and then z3, z4, right? Qubit 1 at p equals 1 does not know, it has not felt anything about, say, qubit 4 yet. If I have a fully connected graph, then qubit 1 is directly connected with qubit 4. And so Z1, it's also exponentiating Z1, Z2, Z1, Z3, Z1, Z4. And so it already has seen the entire graph, basically, um, at just p equals 1. Whereas for a linear graph, like it has not seen qubit 4 yet, right? It has only seen its immediate neighbors and the immediate neighbors of its immediate neighbors at best at p equals 1. At p equals 2, then it can see the immediate neighbors of its immediate neighbors of its immediate neighbors, right? And so on and so forth for larger p. Which is why, like, I mean, the sparser the connectivity of your graph, like, I mean, the poorer your performance, I guess, would be. So that's maybe why, like, I mean, for a fully connected graph, you would probably theoretically see um, a better performance. Now, I should mention on that note, by the way, that in practice, that's not exactly how people, like when people sort of like, I mean, when I say people, when people like us at Rigetti, when we try to demonstrate QAOA, typically we might not do like a fully connected graph. We might do something like a linear chain graph. And the reason why is because the linear chain actually respects the topology of the chip, right? So like typically, physically, we don't have like a fully connected qubit lattice. We only have, our lattices look like an octagon, several octagons connected to each other, but you could sort of select the linear sublattice somewhere along that. And so that linear sublattice can be like, that's something that you can sort of like natively match a QAOA problem to, right? So it's easy to sort of implement that. Whereas if you try to compile a fully connected Hamiltonian down to a linear sublattice, then you run into swaps and all those other things, right? So all those other complications. Uh, so that's why, because and swaps can get pretty expensive pretty quickly. So even though theoretically, you might be able to get better performance on a fully connected graph, in practice you often don't because of the swaps and because of the compilation overhead. But yes, like the point that this exercise was supposed to drive home was that you don't really see, other qubits um, until like larger values of p. And that point actually was driven pretty well, I think, home in just the original QAOA paper by Farhi, Gutman, and and Goldstone. So I'll just post the original QAOA paper over here as well. Um, and it's a pretty, I would say, like, I mean, as far as quantum computing papers go, it's a pretty readable paper. So I would really encourage you all to go through this paper. There's, the part that I'm talking about over here is like, um, yeah, literally, like this is on page 4, like a fixed P algorithm, and it, just goes into Farhi, by the way, is like, you've got to love how he writes. Like he writes it like in a very sort of like conversational way almost. Uh, so yeah, just go through it, and I think it'll be a fun read if nothing else. But like basically this point that I was just describing of like how for any p we see that the operator only involves edges at most p steps away from the particular edge that you're considering and qubits on those edges. Like that's basically why it will take some significant number of p steps if your qubit is sort of like limited in its connectivity, if your graph is limited in its connectivity.
So does error come into play into this computation when you trying to test chips or whatever? So there must be some error, right? So how do you guys do that? Just using what we learned today, like the
So when you say that there's always errors, you mean there's always errors on our QPUs, on our devices?
that there must be few errors, right? So when we're using these techniques there, like using a fully connected graph that you mentioned, right? So if we're doing that on an actual QPU, uh, then we would need to do some error mitigation, right? So
Correct.
these techniques combined together, like what we studied today, we use those techniques there.
I'm only able to make out about like 20% of what you're saying, by the way. But
But louder, I just meant that when you're testing the chips that we discussed last time, right? You showed us that the diagram for like that for testing the chips. I was just curious whether there was errors obviously in that actual QPU that you do and the chips that you're trying to test. So how do you guys mitigate those kind of errors? Are you using all these techniques?
oh, I mean, exactly the way that we discussed today, right? So like not exactly, but this is one way in which you could certainly mitigate those errors. So for example, readout errors, uh, you know, like so the method that I described in practice today, this isn't exactly how we do it. I mentioned briefly, like, I mean, using like readout symmetrization and then calibration. But that is also a technique that like in usual cases scales exponentially. We only use it because in some cases it scales, it may scale polynomially, uh, which is why it sort of gives a computational advantage. But if you do, the sort of readout error mitigation that we described earlier today, um, that will mitigate for the readout errors on our QPUs. And we do that sort of thing all the time, especially for something like QAOA, where like readout errors alone can account for a lot of the errors in the landscape that we might see. So in the notebook, I'm pretty sure we produced a QAOA landscape. Yep. Yeah. So like this was like a two-dimensional grid across the gamma beta values, right? So a lot of the times, like sometimes we're not really interested in looking at just the QAOA cost function landscape, but some other specialized type of Hamiltonians that are derivative of the cost function. Um, and like I mean, we've definitely like this is as recent as a few weeks ago, where we were doing an experiment involving the XY gate, which we are literally like we just rolled out a few months ago at most. Um, and one of the experiments that we were running was like, okay, we wanted to make sure that this thing called the Hamming weight is preserved across the XY gate. Um, and so one way to do that is to measure the sum of all Z observables across all your qubits that the QAOA algorithm is working on. And when we actually computed the expectation value landscape, like, I mean, like it was ideally, it should have come out to be like a flat one or some value that we, had computed, or which is basically the value of the starting state. But this was coming out to be a whole zigzag, right? And so this was a mystery for some time, like, okay, why is it doing this? But turned out it was all primarily because of readout errors. And so if we just, as soon as we mitigated for readout errors, most of that stuff disappeared. Um, and when it comes to gate error mitigation, the sort of stuff that I just described, that's like definitely a big part of that. That's a now, the one big caveat is that, like, on a physical QPU, the noise model is very complicated. It's not as simple as a depolarizing channel. But I also mentioned, and it's still true, that there are lots of ways to sort of turn whatever noise channel you have into something that basically looks like a depolarizing channel. And that's something that we do all the time. So we report, when we report our gate fidelities, we use a process known as randomized benchmarking. And in randomized benchmarking, the idea is that you'll basically turn whatever noise channel is on your physical device, and you'll turn it into a depolarizing noise channel. And once you've turned it into a depolarizing noise channel, then you have all the nice properties that we discussed, which is that the probabilities exponentiate when you pass them, when you pass your qubits through sequential um, noise channels, and you can sort of use that property to infer how well or not your 2-qubit gate is operating. So that's that sort of stuff we do all the time. So what I presented to you was actually meant to give you a taste of like what's happening today in real time at companies like Rigetti. This is the sort of stuff that, like, if you read papers, on quantum computing, like these are exactly the sort of readout, or sorry, like error mitigation techniques that people use. On our devices, on IBM's devices, on Google's devices. This is exactly the sort of stuff they do. Uh, if you open up a textbook, on the other hand, and you try and learn about error mitigation, you actually probably won't find the word error mitigation. You'll probably find the words error correction, which is why people in the quantum computing community, I guess, tried not to use the word error correction for these sort of techniques. They call it error mitigation, just to distinguish it from kind of textbook style error correction. When people talk about error correction, that's more like the idea is that you're going to produce logical qubits, and there was actually a very impressive demonstration recently by the startup IonQ, where they did produce logical qubits. And you should just Google IonQ logical qubits, and I'm sure you'll find like some good news and blog posts, or in fact, even a paper or whatever. Uh, but yeah, I mean, like that's sort of like the next milestone where the industry wants to head towards, is like you um, eventually, like quantum computers, like we know that like once, like how quantum computers, like whether they're going to be useful or not, like in this kind of near term where we're using these kind of like clunky techniques like error mitigation and using these algorithms like variational algorithms and stuff, like it's unknown whether that's going to really deliver quantum advantage. But we know that like once we have logical qubits and we have error correction, um, that's going to be an era in which we will, be seeing quantum advantage for sure. But it's a long ways till we get there. So in the meantime, this is the sort of stuff that people use.
You mentioned the process that you use for figuring out fidelities, for reporting fidelities in terms of random benchmarking. Is that a norm across all the quantum startups, that this is the way that you calculate fidelity so that they're comparable to each other?
Yeah, it's pretty standard. I mean, like what if you talk to QCVB experts, of course, like we always run into the folks who are actively researching on this, and they'll always tell you, oh no, you shouldn't be doing randomized benchmarking, like you should be like doing this, like it has this and this, because like we found this and you should read our paper, and we've implemented this, why don't you try our code? And so we do those things, and we invite academics and other people to sort of like benchmark our computers in novel ways. But RB is totally standard. Like, I mean, everyone knows what we're talking about when we say, like, I mean, everyone trusts that word, like, or that I guess that metric or that measure of performance. So it's a totally standard way of doing things for sure.
Thank you. I don't think there's any question here.
Okay. So I will try. I will try to get you the solutions in. Looks like it probably might not happen tonight, but I'll try to send them in before the next session, Gibran, if that's okay.
So I was planning it is to essentially wait till 1 week before sharing with the students so they get a chance to work on it, and then
Oh, perfect. Okay,
So
that gives me some time to prepare the solution myself. Good. Cool. All right. And what I will do probably what I will try to do a little bit sooner than that is also share an exercise on the gate error mitigation. For some reason, when I was preparing it, like I kept on getting some errors, which I don't know if that's a Pikewell bug that's been introduced recently or something off in my own Pikewell setup, but I need to look at that a bit more carefully. But then I'll share with you all.
sounds good.
Cool. All right.
Thank
Well,
you.
yeah. Thanks for having me. Take care.